Last time we started to talk about the Fourier series representation for discrete time periodic signals. Okay, so in particular, we're interested in periodic signals that can be represented in this fashion, right? Represented as a linear combination, of the set of harmonically related complex exponential signals. Okay. Now, what's different from the continuous time case is that in discrete time, the set of harmonically related complex exponentials is finite. Okay, so in particular, if you're looking at these complex exponentials with period capital N, then there are only capital N distinct harmonically related complex exponentials. All right, so when you write this Fourier series representation, there's only the need to sum over capital N consecutive terms. Okay, so this is in contrast to the continuous time case where the summation goes to infinity, right? Because each index represents a different complex exponential in the in the continuous time case. Okay. Now the question is, does there exist a Fourier series representation for all discrete time periodic signals? And the answer is yes, because because asking whether or not this expression exists for all periodic signals x of n is equivalent to asking whether or not you can find these coefficient values such that this equality holds for capital N consecutive values of x. Okay, and because what this gives you is a system of linear equations where you have capital N equations and capital N unknowns to solve. And since these linear equations are linearly independent, therefore the solution must always exist and is unique. Okay, so just by looking at this system of linear equations, we can infer that a Fourier series representation exists for all periodic discrete time periodic signals. Okay. So then we went on to look at a few examples. Right. So we looked at the case of a pure sinusoid. And through these examples, you can see that indeed the Fourier series coefficients are periodic as well in terms of its index. Okay, so the Fourier series coefficient values start to repeat itself every integer multiple of capital N. Okay, so it's sufficient to just look at only a window of capital N values. Okay. Right. Now, similar to the continuous time case, you can also derive some basic properties of discrete time Fourier series, and these properties will help you, make computations, these Fourier series computations, more easier for more complicated cases. Right. So using these basic operations, you will be able to compute more easily, complicated Fourier series representations. Okay, so the derivation of each one of these is, rather straightforward, similar to the continuous time case. So we're not going to go through their derivations. Okay, but we can, look at a few examples. So in particular, we have in the following multiplication, the first difference, and the Parseval's relation. Okay, so we're just going to quickly go through these three as an example, but for you should go back and try to derive each one of these yourself, just by the just by applying the Fourier series representation that we gave at the beginning. Okay, so all these derivations are rather straightforward, similar to the continuous time case. Okay, so let's go through this, faster, because this is the same, more or less the same as the discrete continuous time case. All right, so again, we can give the shorthand notation here to represent the relation between the discrete time signal and the Fourier series coefficient, right? So there's a double-headed arrow with Fs on the top to represent Fourier series. Okay. Now, for the multiplication property, this is saying that, if you have two signals, xn and yn, with Fourier series coefficients ak and bk, respectively, and that both of these signals are periodic with period capital N, okay? Then you can show that if you take the product of xn and yn, right, this product will also be periodic with period capital N, and that the Fourier series coefficient of this, multiplication signal will be equal to the convolution of the Fourier series coefficients of xn and yn, respectively. Okay. Now notice that here, when we compute this convolution over the Fourier series coefficients, the summation is only over capital N consecutive values. Okay, so this is referred to as a periodic convolution. Okay. So for the first difference property, right, this is saying that if you have a signal xn whose Fourier series coefficient is ak and is periodic with period capital N, then the first difference equation, which is x of n minus x of n minus 1, would certainly also be periodic with the same period. And the Fourier series coefficient is equal to this given here. Okay. Now you can derive this using the linearity property, right? You can first compute the Fourier series coefficient of xn and the Fourier series coefficient of minus x of n minus 1, and then add them together to get this. Right. So you can see here that, this second term here represents a time shift in the time domain signal, right? So if you recall, right, similar to the continuous time case, a shift in time of the original signal corresponds to a phase shift in the Fourier series coefficient. Okay. Now we also get a similar Parseval's relation, which states that, on the left-hand side, which is the average power over one period, this is the average power of the signal, okay, should be equal to the sum of the average power of each of the harmonic components. Okay, so in particular, AK absolute square is the average power of the kth harmonic component. Okay, so summing up all the average power of all harmonic components, we then get the average power of our signal over one period. Okay, So like I mentioned at the beginning, the reason for deriving all these basic properties is because knowing these basic relations help us simplify the computation of Fourier series coefficients in more complicated cases. Okay. So the key to utilizing these basic properties is being able to identify the presence of these basic properties in the problem that you're looking at. Okay, so let's look at a few examples. So these examples are more or less like the examples we looked at in the continuous time case as well. So here we're looking at a signal xn that looks something like this. Okay, so you can see that this signal repeats itself every 5 samples. Okay, so you can see that this is 22211, and then again you have here 22211. Right, so it's repeats itself every 5 samples. So the fundamental period is equal to 5. Okay. Now, by observation, you can see that this signal xn can actually be split into 2 signals. So first of all, we can think of this as having this signal 1, 1, 1, 0, 0, 1, 1, 1, okay, 0, 0, 1, 1, 1, 0, 0, so on and so forth. Okay, plus a signal that is constant 1 over all time indices. Okay. So plus a signal that is equal to 1 over all time. Okay. Right. So if you add these 2 signals, you will see that, let's say for n between -1, 0, and 1, 1 plus 1 is 2, right? And for n equal to 2 and 3, right, 0 plus 1 is 1. Okay. So let's call this signal x1n and this signal x2n. Okay. So xn is equal to x1n plus x2n. Right. Now suppose that xn has Fourier coefficient ak. Okay. x1n has Fourier coefficient bk. And x2n has Fourier series coefficient ck. Okay. So first of all, by linearity, we know that since xn is equal to x1 plus x2, ak must also be equal to bk plus ck. Okay. Now, to first obtain the value of bk, right, if you look at this signal here, you will see that this is a periodic square wave similar to what we looked at in example 3.12. So if you look back to example 3.12, right, in example 3.12, we looked at a general periodic square wave where the square ranges from minus n1 to n1, and it repeats with period capital N. Okay. Now in our case, this is equivalent to having a periodic square wave with n1 equal to 1 and with period capital N equal to 5. Okay. So from example 3.12, for n1 equal to 1 and n equal to 5, right? We can directly take the result that we obtained there to get bk equal to 1 over 5 sine 3 pi k over 5 divided by sine pi k over 5. Okay. For k not equal to 0, plus minus 5, plus minus 10, so on and so forth. Okay. And simply 3 over 5 for k that is 0, plus minus 5, plus minus 10, and so on. Okay, so this is obtained by just taking the result that we derived from example 3.12. Okay. Now, for x2n, x2n is simply equal to a constant. Okay, so only the Fourier series coefficient corresponding to the constant a DC component of the harmonically related complex exponentials would have a non-zero value. Okay. So for x2n, we have only a constant. Okay. And in that case, the coefficient, this corresponds to a coefficient C0, that is just the average of the samples over one period. Okay, and this is equal to 1. Okay, so in fact, this is for all k, that is 0, plus minus 5, plus minus 10, and so on. Okay. Now, if k is not these values, then it must correspond to a sinusoid that would not have any, factor here because the signal is just a constant. Okay, so this ck would be 0 for all k not equal to 0, plus minus 5, plus minus 10, and so on. Okay, so if you take ck and bk, plug it back into this equation above. You can then find the Fourier series coefficient for ak.